Why is it that of all the billions and billions of strange objects in the cosmos, novas, quasars, pulsars, black holes, you are beyond doubt the strangest?
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts in England and Sweden, Matthew Russell and Linn Boldt-Christmas.
Oh yeah, baby. Walker Percy.
Walker Percy, who's that?
Walker Percy was a philosopher, an American writer from Birmingham, Alabama.
Not the real Birmingham, but Birmingham. Sorry, American listener.
Home of legends like myself and Ozzy Osbourne.
Are you from Birmingham?
I am from Birmingham, yes.
How did I not know that?
I don't know, but...
Which one's bigger?
Oh, Birmingham, UK is bigger. Yeah.
Yeah?
Yes.
I mean, I believe you. I don't know why I'm questioning it.
The city of Birmingham, Alabama is something like 250,000, whereas Birmingham, UK is over 1 million.
Oh, well, how about that? I don't know. I just assumed like southern US big things.
No, I don't think Birmingham, Alabama's that big a city.
No.
It's not that big.
And Birmingham, UK is bigger than it is in people's minds.
Well, yeah, well, it's the second city.
Is it
I'm
actually?
sorry. I'm sorry to say that to the people of Manchester who always claim it's them.
I was just about to say, is it not Greater Manchester?
No. Birmingham's just a little bit, just a tad bigger, and it's where the modern world comes from. It is the place where the Industrial Revolution started.
Again, surely Manchester wants to have a word with
they like to think it. Manchester should claim the start of the atom and nuclear power. That's what
I'm sure
should
they'd be
claim.
okay with that. Did you know that in Swedish, corduroy, the material, is called Manchester?
Oh wow, is that right?
Yeah, we just call it Manchester.
Yeah. Anyway.
Yeah, so space.
Space. Is there anything decent in space from Birmingham? Don't know. Well, there's Birmingham University, which has got some fine astrophysicists at it, and it's a very important place for physics.
Birminghamian astronauts, perhaps?
I don't think anyone from Birmingham has been an astronaut.
Also, what do you call someone from Birmingham? It's not Birminghamian, I assume.
It's a Brummie.
Oh, Brummie, of course, the Brummie accent.
The Brummie accent. And of course, most Americans recognise Brummies from Peaky Blinders.
Oh, Jesus, yeah.
Yeah.
I've never seen it. I've only heard.
We need to get back to space, Linn. Come on.
Spacing out, ironically.
Spacing out, unironically.
Yeah.
So before we start, it's a word up to the mega patrons, which are Justin Roberts and Drew Wright. Thank you very much, guys. I cannot tell you how important and how amazing your contribution is to the Interplanetary Podcast. Legends. Hi, Linn.
Hi.
We missed you. We didn't have you last week.
Guys.
We had to have a patron fill in for you.
Oh, lame. No.
I
listened to it. You guys did a great job. I very much enjoyed it.
Thanks. Linn, where are you right now?
Right now, I'm at the famous Angstrom Laboratory at Uppsala University, which is where I work.
It's very cool.
It is very cool. It's named after. So when people who maybe are doing science at university or something, you've maybe seen that there is this unit of wavelength called 1 angstrom is how the anglicized version is. And of course, I was always the nerd when I went to university in England who was like, guys, it's not actually angstrom, it's angstrom. Just to really correct them.
Pipe down, Linn.
Exactly. So the one that is the A with the circle above it, you may have seen it, which is the unit for 10 to the minus 10 meters, which is really useful because there's a lot of interesting sort of electromagnetic radiation that happens around those kinds of wavelengths. So rather than saying like, oh, this is as a wavelength of 4.8 to the times 10 to the minus 10 or something, you can just say like, oh, it's 4.5 angstrom. But it's named after a person called Anders Angstrom. And so the circle above the A actually does change the sound of it. And people think it's just like an accent that you can sort of delete. But actually the A with the circle above it is a totally individual letter in the Swedish alphabet. So it's kind of like looking at a Q and being like, oh, well, that's just a little dash. I'm going to pronounce it like an O. Or looking at a P and being like, or looking at a B and seeing like, oh, well, there's just this little extra thing that's basically a P, right? So no, the A with the circle above it is pronounced totally differently. It's pronounced like an AO sound. So it's Angstrom, because then the 2 dots above the O also makes it a OE sound. Really not to do with space, actually, but I'm really passionate about Swedish language.
Yeah, well, no, fair enough. And the fact that I can see you in your little office there is very, very cool. It's super cool.
It is nice.
It is nice. I'm in Guildford, which of course is the place where they build lots and lots of satellites.
That's true. I wonder how many angstroms away you are from me.
Quite a few.
Quite a few. The joke here at Angstrom Laboratory in Uppsala is that, like, 1 angstrom is walking the length of this building, which is quite a lot more than, because it's quite a long building. That's 1 angstrom. It's not a good joke.
No. I learnt a new little phrase, a bit like the angstrom. It's a measurement of distance called minimum orbit intersection distance. The MOID.
Oh,
do you know this one?
No, I
don't. The MOID. So I found it because Didymos,
yes,
or 65803 Didymos, to give it its full,
its government name.
Its government name. Don't bait out its government name, whatever you do. But it's its Earth MOID is 0.0403 AU. What do you think that means?
The AU as in astronomical unit?
Yeah, I know that you know what astronomical unit means, but having a 0.0403 AU, what do you think that means?
I don't know. Is that the radius?
Yeah, so that would be its minimum orbital insertion distance, minimum orbit intersection distance. In other words, it's a kind of measurement about how dangerous it is in terms of its likelihood to crash into Earth. I think that's
feels
what it's
low
used
then.
for. Yeah, it is. It's pretty low.
Yeah.
So in other words, it's 4% the distance of the sun.
So this is,
roughly,
of course, in the context of DART, which has just happened, the double asteroid redirection test. Oh my God, I'm so excited that this actually happened. Yeah,
do you know what? One of the best things I've seen about that is the European Space Agency managing to do a little film from the ground of it actually hitting.
It's crazy.
It was from the French island of La Réunion.
Yes.
In the Indian Ocean. They managed to capture this kind of sequence of images.
It's so cool.
Almost like in real time, 30 odd seconds later. As we've just heard, they're not that far away.
No.
There's another called LD, which is a bit like AU.
Yeah.
It's only 15 or 16 lunar distances away.
And that's not that far.
Well, it is far.
It's far.
It's just, in terms of the size
galaxy.
of the galaxy, it's nothing.
Nothing.
You're right. It's nothing.
Yeah.
Whereas in terms of the size of the solar system,
I feel like astronomers are really unhinged. Like, we have no sense of scale anymore, where like everything can be so, this tiniest thing, we're like, wow, it's pretty big. I mean, it's bigger than an atom. Or we can be like, oh, well, that's only like a couple of galaxies with.
Yeah, well, I'll tell you what is cool about Didymos. Didymos has a moon called Dimorphos.
Which, if I may interject, I'm really sad because I thought Diddy Moon was a much cuter name. That's what people used to call it.
Well, its proper designation is Didymos 1.
Yeah. Boo. Boo. Bring back the real names. That's my toxic opinion as an astronomer.
Yeah. And dimorphous, of course, means having 2 forms,
which is pretty suitable, actually. All things considered.
Yeah. Well, it's now it's definitely got 2 forms. Now it's been
it's got a couple.
now it's been hit by a great big lump of metal.
Yeah, I love that. For once, we were able to crash something into something and start clapping.
Yeah. Oh no, it's not. I mean, it's not the first time it's happened, though, is it? The Americans have crashed things into comets before, haven't they?
That's true.
Mm-hmm.
We bounced things off of comets before.
We have.
Let's not talk about it.
Yeah, we have bounced things off comets. The Europeans have landed things on comets.
That's true.
So,
we've even got things back from comets. JAXA, right?
Oh my! Yeah, JAXA's done it.
Or
NASA have done it as well.
Yeah.
In fact, NASA are in the process of doing it again as well.
God,
in fact, the Japanese.
Boring.
Yeah, it's actually getting boring now. But this is all about planetary defense, though.
Yeah. This one's for the dinosaurs. This one is taking one for our ancestors, our lizard ancestors.
Yes, exactly.
Finishing business. Maybe the dinosaurs can finally stop haunting us because we've finished their unfinished business. in
So, okay.
figuring out how to get rid of asteroids.
So how does DART help us get rid of asteroids? Go on then. The threat of asteroids.
The threat of asteroids. So the idea of it is that we wanted to test, in simple terms, if we were to spot an asteroid hurtling towards Earth, don't look up style, could we smashy something into it to change its course, to make it go somewhere that isn't Earth? And so we've done a smash into it. And what we're checking now is to see by how much we were able to deviate its course, and then to see if that is sufficient. I mean, all of this will depend on like how big is the asteroid, what kind of density is it? You know, if you imagine asteroids and comets, they can be anything from like a sort of ashy snowball to like a proper rock. So what material it's made of as well is also a big question. But this is like the first time, I think, right, that they've done like a really proper, we're doing this for redirection. That's what the R in DART stands for.
Yeah, exactly. So they're trying to, push it away.
Yeah.
And I suppose, like, if you do anything that's when it's far enough out, then by the time
exactly,
you don't have to move it that much.
Precisely.
But then I suppose you might just be kicking the ball into the long grass, because you push it out one time, and then when you look at it again, it says, it's on a collision course for 60 years' time.
Yeah, but you know what? When it's the 89th minute, you just kick that ball away from the goal.
That is true. Well, that is exactly right. Yeah. It's like kicking a ball. Yeah. It's like it's kicking it behind, isn't it? Really?
Yeah. And it's just like hoping there won't be overtime.
And now the asteroids have got a corner.
Exactly. But then, then at least you have 60 years to prepare for a bigger, better, more violent redirection, right? So
I suppose so.
It's a hypothetical scenario at this point. I mean, hopefully we'll never have to use this technology.
Oh, well, we'll definitely have to use this technology. I mean, that's almost like a given, isn't it?
Yeah,
we might not have to use it. Yeah, we might not have to use it in our lifetimes.
Yeah. Exactly.
Although I do plan on living forever, Lynn.
Excellent.
I hope you realise
cool.
That. Yeah, but
climate.
Yeah, I've got podcasts to make.
It's true.
It's true. So, but we will have to at some point, because Chicxulub killed off the dinosaurs, as we know, and it's only a matter of time.
Do you want to hear? Do you want to hear a cool fact about that asteroid? I don't know. I don't want to like put my reputation on the line here. But I did actually, for an outreach talk I did recently, I figured out, using a number that I used for my old master's thesis, about how many of those asteroids would have to smash into Earth at the same time to release as much energy as a supernova.
Well, presumably it's billions and billions.
It's a really big number.
Well, I do know one fact, and that is that the Chicxulub explosion was more than 1 billion Hiroshimas in energy.
Well, but in terms of supernova, do you want to know the number?
Oh, go on. Now you've got it.
10 billion, which is then 10 to the 19, which, in case you're wondering, is about 20 times more than there have been seconds since the Big Bang. It is an illegally large number.
Yeah. 10 billion. So a supernova is 10 billion nuclear bombs.
Something like that, yeah.
Yeah, which then becomes ridiculous.
Dumb. Just like too many zeros. I can't count that high. 19 is way too big of a number for me to count to.
So that would be 10 to the 28 nuclear bombs.
Yeah. So I do feel like the dinosaurs would have been very grateful for a planetary defense system that would have protected them from this fate. So that's why the DART, it's for the dinosaurs. It's for the dino bros.
All that work by people like Angstrom and all the people that went before him and her and everyone else that sort of, part of the human mission. We can't let them down by having all that lost, can we?
Absolutely. And I mean, I just think it's so cool. I just think it's great as well that there's like an actual genuine endeavor to do it. It's not just like a science fiction funny plot line, but it's actually like, we should have some kind of defense for it. So I think it's really cool.
Well done, NASA, because that apparently looks all
right. But we now do have the next chapter begins now, because now it's the ESA part It's not launching until 2024, I believe.
October-ish, isn't it?
Yeah, exactly.
October-ish, yeah. On an Ariane 6.
Is it actually? I didn't know that.
Hopefully
Amazing.
that all goes well
Yeah.
in the new year, so that happens.
Hopefully,
Because
yes.
that would delay it. Because that would definitely delay it if it doesn't happen.
Oh, yeah, for sure.
Yeah.
And I don't know how vital it is that they catch this launch window. But anyway, so now that the smishy smashy bonk has happened, it's time for technical term. Apologies. Now there's this probe that ESA is sending out, which I guess it's Hera. Hera. It's the Greek goddess.
We decided both were acceptable.
I think, yeah.
Hera and Hera.
Should I say both at the same time? Hera.
Yeah, there we go.
The H
Who knows
dog.
how the Greeks would have said it?
Do you know
The
any
goddess
Greek
of marriage.
If there are any Greek people listening, do let us know. and rate our Greek out of 10. Or maybe don't, to spare our feelings.
No,
But-
don't. Please.
Please don't. But yeah, no, so this is a probe that ESA is sending up. And so they're going to perform a post-impact survey of what's left of the poor bastard. Which is great because, I mean, this is also yet again just another great chance to study solar system bodies.
Yeah, and it's going to be carrying a couple of little nano satellites.
Exactly.
Milani and Juventas.
Probably also correctly pronounced.
That's going to be really exciting because that is a humanity first of a satellite actually going out to a binary asteroid and getting into orbit along with it.
I feel like roundabouts are scary. So like this is really taking it to the next level.
There's a brilliant ESA picture of it being just right above the Colosseum. So it's about the size of the Colosseum,
like
the little moon. So
Yeah.
how big do you think Didymos is?
God, bigger than the dinosaur killing one.
Is less than a kilometer.
Really?
You know, it's getting into orbit with something that's pretty small,
Yeah.
but still pretty big.
Yeah.
It's pretty impressive,
Again,
isn't it?
astronomy.
Astronomy, engineering,
Yeah.
rocketry. Yeah, I mean, it's just really impressive that you can even attempt to get something into orbit around something that doesn't even look like a grain of sand from Earth.
It's nuts. I'm yet again in awe of what humanity can achieve. As I sit drinking tea.
It's a bit like sending a spacecraft out. If you could see the Colosseum, if it was 15 times further away than the moon.
It's dumb.
You know, work out all the orbital mechanics of chasing it down and then getting into orbit around it with enough fuel. It's very impressive indeed. Do you want to hear what the Hera mission manager said about the DART impact?
I would love to.
His results from that will prepare us for Hera's visit for a Didymos binary system to examine the aftermath of the impact. A few years from now, Hera will help us understand what happened to Dimorphos, the first celestial body to be measurably moved by humankind, and ultimately protect ourselves from space rocks that one day could do the same. There we go.
So what part of Birmingham is he from?
The Italian quarter.
Oh yeah, of course. Little Italy.
Yeah. It's another one of those brilliant little international collaborations.
It's amazing. I love the fact, I don't know if maybe I'm too young to remember a previous time, but I think it's so great that I really feel like space endeavors are becoming more and more and more and more collaborative and international and all this stuff. I think it's amazing.
I've got a really good guest.
Oh, have you?
On here. Yeah. So I've got Dr. Becky. That's how most people know her.
Dr. Becky.
Or Dr. Becky, 500,000 subscribers on YouTube for for an astronomy, you know, a serious astronomy YouTube channel.
That's amazing.
That's pretty impressive.
That's very
pretty
impressive.
impressive. Yeah, so she's a junior research fellow at the University of Oxford.
Oh, yeah.
Yeah. A recipient of the 2020 Caroline Herschel Prize lectureship.
That's very cool.
She 2020 Mary Somerville Medal and Prize awarded by the Institute of Physics. Won the Royal Astronomical Society's Winton Award for research by a postdoctoral fellow in astronomy whose career has shown the most promising development.
I feel deeply insecure.
Yeah, you're out, Linn. Becky's in.
Yeah. You know what? That's fair enough, actually. I would replace me too.
And I've read 2 of her books now. So I've owned for a long time her book Space 10 Things You Should Know, which is it's a small little book and it's really cool.
Cool.
And she's just written a new book out on the 1st of September called A Brief History of Black Holes, which as you'll hear is her attempt to kind of address all the things that people get wrong about black holes, like black holes are like vacuum cleaners sucking everything up, all that kind of craziness.
Classic ones.
I cannot recommend her channel enough. If you see a James Webb image, then there's a bunch of stupid like news articles about it. Then normally Dr. Becky's pretty quick at putting up a kind of YouTube response, and it's always very, very good. Always
that's really good, and
gets
that's also
to the heart of the matter.
That's really good, because especially like sort of misinformation. I mean, that's a strong word actually, but a lot of the time people do. I saw the other day, I was trying to find a picture of Europa, and I found a YouTube video that was like pictures from the surface of Europa, and they were like basically a sci-fi video game with a huge Jupiter in the background, and I was like, wow, cool. Didn't know we just had landed already and got loads of HD pictures from there. There's a lot of stuff like that. I'm not going to call it misinformation, but having people to clarify what's real and what's not real. Because I mean, really, the truth is the most impressive thing there is. So.
Yeah, well, it's quite frustrating because I was on holiday in Greece quite recently.
Oh yeah,
going back to the Greeks, and it's quite funny. As soon as you say, "Oh, you meet someone," they say, "Oh, what do you do?" And you say, "Oh, I've got a little space podcast."
Yeah.
Oh, I'm really interested in space, and then they'll recount some recent news story they've seen. Oh, apparently they found a new water world, and it's like, well, yeah, they have, but. Is it? It's just like it's like, and so it almost seems that when you're trying to tell the truth, you sometimes kind of ruin the kind of romantic bubble that the kind of less scrupulous press will use.
You know what I think it is? I think it's because the scientific truth, it's not very snappy. It's everything but. It's elaborate, and it's layered, and it's nuanced, and that's not very impressive in the same way. It's much easier to take something and then like package into a small thing and be like, we found a water world, rather than like, we found a potential candidate that does seem to show some sort of detection of water vapor in its atmosphere, but really only within this many sigma. Like, it's not that. It's not that sexy.
It's not that catchy. It's not that catchy, is it?
And so,
but you run the danger of putting people off, because then they always come back with that stupid science keeps changing its mind on things. And it's like,
that's what it's supposed to do.
It doesn't. It revises its mind on things.
I think you'll find I still like the way that I am orbiting with the sun orbiting the center of the Earth. Thank you very much.
We are stupid scientists.
Thank goodness for people like Dr. Becky.
Well, exactly. Dr. Becky, in all seriousness, she is a bit of a sort of science sci-com hero of mine. Very, very, very cool. So it was really, really good to get her on the podcast. So would you like to hear it?
I would love to. Let's hear it.
Okay. Aikute.
The Interplanetary Podcast, putting the ace back into space.
So I'm joined on the podcast by Becky Smethurst. Welcome to the podcast, Becky.
Thanks for having me. I'm thrilled to be here.
Becky, loads of people that listen to this podcast will know you because you are pretty big on YouTube. Before we get on to black holes and James Webb, etc., tell us a little bit about how you sort of started your science communication rise to fame.
I wouldn't put it like that, but okay, yeah. So, I mean, I'm an astrophysicist. I'm a researcher. I study supermassive black holes, but I've just always loved to chat about space. And I think I've had, like family and friends that have just generally been curious about what I do as well. And so got used to, explaining it to them in a way that they could also understand as well. That, wasn't just a conversation with my colleague. It was, almost like a different language that you had to speak to be able to communicate with family and friends, just so they understood, what I'd gone off to do. And so I realized that I actually really enjoyed that aspect, almost the challenge of how do I explain this so that they can understand. And I never really lost that through sort of my university career and then getting my PhD and going on to be a researcher. So I realized that YouTube was just a really great platform to have a chat with people. You know, you could do a quick 10, 15 minute video about something. People would post comments. You'd be able to answer their questions. And so it's just really grown out of this love of chatting space, which I'm sure you obviously recognize as well with the podcast.
No, absolutely. I mean, it's exactly the same as how, why I do it, really. Because I'm always explaining to my friends that those aspects of stuff. I mean, were you surprised that you got as many watchers as you did?
A little bit, yeah, because I'm just chatting away in my spare room, mostly through the pandemic as well as something to do. And it really took off from there. So I did actually get my start on YouTube through a different channel actually as well. I don't know if people are familiar with 60 Symbols. Brady Haran runs it along with like Numberphile and Computerphile, all these big channels. So I got my start there when I was at the University of Nottingham. It was a position that was basically, we've got some research money available, but if you want it, you'll have to make videos for 60 Symbols too, which was great fun. And after I finished up there, I decided, my own channel is something I want to start up too. And I think people maybe have sort of recognized me from there, and that helped growth and everything like that. And now, we're very nearly almost at 500,000 people. And I feel like, I'm used to big numbers every day. I study supermassive black holes, so it's probably the biggest numbers you can get. But I don't think I quite realized how big that number was until my dad said to me, you could fill Wembley Stadium 5 times over and have some people spare, which is insane. So
I know I do exactly the same thing when I'm sort of talking to people about what does the podcast look like each week, and it's like if it was in a auditorium, that would be, you'd be very impressive. So I mean yours is Rock in Rio, isn't it? I mean, that's just insane, insane numbers. That's really encouraging, isn't it? Because you don't mess around really, but you sort of, but you also don't kind of do the super flowery stuff or the super kind of going over the top with things. It is really kind of saying how it is, while at the same time keeping it pretty exciting. So those numbers are super impressive.
Yeah, thanks. I mean, I always didn't like that about documentaries when I was watching them, just I was like, get to the point, the graphics are amazing, but I want to hear what it is. And the thing that frustrated me as a kid was I didn't just want to learn facts. I didn't want to learn what we knew. I wanted to learn how we knew something. So that's definitely always a focus I have on my channel is, okay, so this is how we figured this out, or this is the person that figured this out in history, 100 or 200 years ago, or whatever that is. And that's why we have this idea now and not something else. And I think understanding that really, really helps people understand the why of things now.
Yeah, I think that's super important. I always think a really good starting point with things like things, especially black holes, is the history of them, because how we get to how we know about them it is actually quite ridiculous, isn't it? I mean, it
really is. It really is.
So with that, take us on a journey then, because obviously we start with Einstein, and it's kind of almost like a sort of mathematical sort of anomaly, really, that comes out of it. So Einstein himself, though, never even heard the phrase black hole, did he?
Nope. And he never even predicted their existence. It was not something he was ever involved with. And I think that's one of the many misconceptions people have about black holes to start off with as well. So when you think about the history of black holes, I love to remind people of those sort of almost that chronologicalness of also how young the field actually is as well, because it is something that feels like it's pervaded sort of the psyche for a while, but it's been a long time coming. So even the phrase black hole didn't exist really until the late 60s in terms of both public and the scientific community. They were referred to as gravitationally completely collapsed objects, or GCCOs, which I always joke, if we do the modern day thing of astronomy and making an acronym, that's what we'd all say we'd be working on, and it would sound terrible. But it's one of those things, getting the order of it right. Even thinking that we landed on the moon in 1969 before we realized that the center of the Milky Way, that all the stars in the Milky Way are orbiting, is a supermassive black hole. Hell, even before we'd observed the first black hole and found the first evidence for a black hole in the universe as well, which was sort of towards the late 70s. So it's incredible to think how much research was done by the likes of Hawking and Penrose on those weird mathematical curiosities of singularities, this point in space where you couldn't define how strong gravity was, because essentially you had to divide by 0 and your maths just completely imploded. all of that work was done before even black holes were found or understood to be real objects. They were always these strange hypothetical curiosities that, for example, Arthur Eddington, a giant of the physics world, right, in the early 20th century, he argued, like, to his death almost, profusely against this idea of a black hole, this almost gravitational collapse of, say, the end of a life of a star. He would said there has to be some law of physics that exists to prevent this unnatural thing from occurring. And it was essentially Hawking and Penrose that went, actually, it would be quite natural for it to occur in physics, in nature. And so we've come a long way from the early 20th century.
Yeah, indeed. In fact, Roger Penrose, his Nobel Prize that he only got a couple of years ago, wasn't it? Was that for that particular work that he was doing? Would Hawkins have shared that with him, or was it more of a Penrose thing? Do you know?
I think he probably would have if he'd perhaps been alive. Hawking and Penrose really did that work together on proving that, this idea of how we mathematically describe a black hole and this singularity were natural and would exist. And that Penrose ended up sharing it with Genzel and Getz, who were essentially the first people to look at the very center of the Milky Way, look at the stars orbiting the very center, and from their orbits work out how massive the thing was in the middle that they were orbiting around, and essentially got a number that was 4 million times the mass of the sun, which at the time there was a lot of arguments about, could it be a swarm of black holes? Because we can't see anything that's there. A swarm of black holes would be incredibly unstable. So the only other option was a supermassive black hole. And that was the late 90s, early 2000s. That was the only time that we then were like, there's a supermassive black hole at the center of the Milky Way. And if we think about how young, therefore, this field of supermassive black hole studies is, I think that really puts it into perspective. But I think it's really great that they then shared that prize with Penrose, who did, the early graft work almost in the 60s. Yeah.
So was the thing that precipitated that Nobel Prize, as in, this is a thing now? Is it the photo of the black hole? Is that one of the sort of pieces of evidence that everyone was sort of waiting for? In terms of, we can give this Nobel Prize out. Why the wait? I mean, I know it's recent, but why a 20-year wait before they sort of dish it out?
The image was of the supermassive black hole at the center of a different galaxy, so Messier 87, rather than the center of our Milky Way galaxy, which we actually only got this year because it turned out to be a much more difficult image reduction because there's lots of dust you have to look through to the center of the Milky Way that complicated things. But I think, that image was essentially like, this is the prediction that general relativity gives us, and then here's the image we got, and hey, they look almost pretty much identical, which is incredible to see. And so I think that was really what precipitated it, was this confirmation almost that we see this shadow of this black hole, this almost prison where you're not getting any more light from because the light's being trapped inside of it. I think that was almost the confirmation that, yes, okay, this is the sort of the last thing, the observation, because you'll notice that with Nobel Prizes is that you can have some theoretical prediction, like, for example, the Higgs boson in particle physics, something like that, but the prize won't be awarded until you have this observational confirmation of something being true. And black holes was this area of astrophysics that had never been ever sort of recognized by the Nobel Prize Committee. And so seeing that recognized finally, I'm sure that was a massive decision for them on who to recognize, because there's obviously a lot of people done work in this field. But recognizing that it was the work done in the center of the Milky Way that was really the concrete evidence that we had for supermassive black holes and black holes in general existing was really great to see that recognized.
As a kid, I remember people talking about black holes. And obviously there was a few films that came out in the 70s and early 80s about black holes and things like that.
Yeah.
But they were still considered a kind of, they don't really exist. They're sort of just particularly when it came to things like wormhole versions of it. But
well, yeah, this is the thing. They're so often confused with wormholes. And I put this down to basically like sci-fi in the 80s and 90s, just using them interchangeably. And it's like, no, they could do completely different things. One hypothetical and one actually observed.
Yeah, but I guess back in the 70s and 80s, they're both really this in the same category there, because they're both hypothetical, aren't they? I mean, it's at what point do you think, in terms of your community, in terms of the astrophysics community, you started to feel as though no, the black hole's is not hypothetical. It's obviously a real thing.
I mean, I didn't really live through it. I really only joined the community in 2013 when I sort of started my PhD. So almost to me, I use the phrase, there's a supermassive black hole at the center of every galaxy. I take it for granted. It's just this phrase that is and was and always will be, which is obviously not the case. But I mean, looking back through the sort of history in terms of the publications that were being written at the time, I think there was this almost inevitability of black holes' existence, definitely through the sort of late 80s, early 90s, in terms of smaller black holes in the Milky Way. So these things that are formed at the end of supernovas, and the inevitability around the late 90s, early 2000s of supermassive black holes at the centers of galaxies. And I think it was just one of those things that just there was just overwhelming evidence for it, that it wasn't something that you could really deny at the end of the day. And it was just sort of a big snowball, essentially, from discovering the sort of first candidate black hole that was, formed from the death of a star in a supernova, to the supermassive black holes at the center of, say, the Milky Way in the early 2000s, to the point where, people were hedging their bets through the 90s. So supermassive black holes, for example, were referred to as massive dark objects, MDOs, again, I guess, if you want. And you see that all through the 90s, and eventually that acronym shifted to SMBH, supermassive black hole.
Yeah. So do people know how supermassive black holes form, or is that still a little bit of a mystery?
A little bit of a mystery, yes, because the only process that we know forms a black hole is a supernova, the death of a massive star. So the outer layers of the star get thrown off, and the core will collapse down into a black hole because there's nothing to resist gravity anymore, because there's no longer any nuclear fusion resisting that push inwards, pushing outwards. So the mass of a black hole that you would form in a supernova would be anywhere from, say, 3 to 4 times the mass of the sun, all the way up to maybe 30, 40, 50. We're not entirely sure of the upper limit. There are some suggestions that stars can just collapse straight down into a black hole as well, from recent observations as well. So that could be anywhere up to maybe, let's say, 100 times the mass of the sun. Getting from that mass up to millions to billions of times the mass of the sun is the interesting question, especially because we see these supermassive black holes only 1 billion years into the universe's lifetime. And the question has always been, there is literally not enough time to have grown a black hole from, say, 10 times the mass of the sun to 1 million times the mass of the sun in just 1 billion years, in that time frame. Because this is the other common misconception about black holes, is that these endless hoovers, vacuum cleaners, just sucking everything up. But actually, most material will just happily orbit a black hole, in the same way that most material in the solar system just happily orbits the sun and is not falling into the sun. So it's very difficult to grow a black hole. And there's been sort of these ideas of whether maybe we just don't understand the growth of black holes in the early universe, and maybe they can grow at a greater rate than we ever thought they could. And maybe that would be the case. And so it's this sort of like chicken or the egg scenario that we've currently got going on in terms of how supermassive black holes form at the centers of galaxies. Do you have a galaxy of stars form first? One goes supernova. That grows its black hole and becomes the heaviest thing in the galaxy and sinks to the center, and then from there grows to become supermassive in some process we don't quite understand. Or do you have a gas cloud in the early universe that collapses straight down into a black hole, skips becoming a star, somehow, is stopped from collapsing into a star, and instead reaches this critical mass, at which point it collapses into a black hole? Then that becomes this sort of gravitational shepherd for everything around it, and a galaxy of stars will form around this black hole.
Well, I mean, that is a pretty big distinction, isn't it? I mean, that presumably is. I mean, that must be one of the sort of biggest questions in cosmology, surely, that you've got.
Maybe not in cosmology right now. They're very distracted at the minute by trying to solve their big model of the universe. But in my field, 100% yes. Okay. It's the big question that we all want answered, because if there was this direct collapse scenario, you would probably start with something that was maybe 10,000 times the mass of the sun, in which case you could grow to supermassive black hole status in the time that's available. And it is something that we hope the James Webb Space Telescope will be able to answer. It's been designed to see back to these first stars and first galaxies forming. And if you do have this big cloud of gas that's somehow being stopped to form stars, it's probably going to be very hot, because rather counterintuitively, you need cold gas to form stars because the molecules can't move very fast. Otherwise, gravity won't be able to clump them together to become dense enough to start nuclear fusion. So if you've got instead a very hot, big cloud of gas that's just drawing in more and more stuff from around it because it's a very large amount of stuff in the universe, and so gravity is sort of starting to take hold, a hot gas will probably glow if it's got maybe some nearby stars that are irradiating it with ultraviolet light as well. So we're hoping to be able to see that sort of glow of these big gas clouds. And there has been some hints with the Hubble Space Telescope. There was something called Cosmic Redshift 7 or CR7 that was sort of nicknamed by the Portuguese discoverers of this object because it's Cristiano Ronaldo's 7 his number. Yeah, that's where the name comes from.
No.
And I think it's quite funny actually. So they sort of found hints that could be this sort of gas cloud that could directly collapse into a supermassive black hole. And so we're hoping with the James Webb Space Telescope, it might be able to find more of these things, more study on them to figure out what they actually are and whether they really are maybe the progenitors of supermassive black holes. And finally answer this question of, did the galaxy form first or the black hole form first? The astrophysics chicken or the egg.
with James Webb looking at these early stars then, is it the early stars as well? Because I remember a previous guest was sort of saying that the very first set of stars that came along, not much is known about that, and of course Hubble's not powerful enough to see them. Is James Webb going to be of that sort of order of power that he's actually going to be able to sort of make head nor tail of those kind of first stars, and therefore is that part of that answer towards your black hole conundrum?
Yeah, I mean, that's exactly what Webb's been designed for, is essentially to see what we call first light in the universe. And really getting to grips with, okay, well, what were those stars made of? I mean, we presume it's almost pristine hydrogen gas, essentially. And if that's the case, can they somehow burn more efficiently in terms of nuclear fusion? And in which case, can they therefore be bigger than stars today? And maybe that might be a shortcut for making larger black holes, because these things could then direct collapse down as soon as the fuel runs out, essentially. And you would maybe start with something that was 1,000 times the mass of the sun, but you had a star that was living its life like that as well, that could collapse into a black hole. So there's lots and lots of questions there. And yes, because James Webb has been designed to have this bigger mirror, so it can collect more light because of this bigger mirror, in which case it can see fainter things, therefore further away things, therefore see the light that has been traveling the longest, the furthest distance. But also, we have to remember that the light that has been traveling the greatest distance in the universe has also been redshifted the most. So there is physically a limit to which the Hubble Space Telescope, viewing the universe in the optical sort of spectrum, the visible spectrum that we see with our eyes, it cannot see at a greater distance anymore because the light has been redshifted so much to longer wavelengths that it's no longer visible light. It's infrared light.
And so is that redshift caused by the expansion of the universe rather than anything else?
Exactly. Yeah. There is some contributions from the fact that this light will go past quite massive galaxies as well. So you'll get what's known as a gravitational redshift, which also happens around black holes too. But the majority of the redshift will come from the fact that the universe is expanding. And so from the amount of expansion, from the amount that the light is redshifted, which you get sort of from these very handy marker points where you have molecules giving off very specific wavelengths of light at these huge sort of like peaks of light. If you split it into a spectrum and sort of draw this trace of how much of each wavelength you're receiving, you can then pinpoint, oh, that's given off by hydrogen gas at this wavelength normally, but now it's been redshifted to this wavelength. Wow, this galaxy of stars is this far away. And that's how we get at that overall redshift of these galaxies as well. So it's incredible, the redshift. So we don't sort of talk about it in terms of distance or light travel time amongst us astrophysicists. We will say, oh, this galaxy is at redshift 7 or redshift 8 and stuff like that. And with Hubble, we were pushing sort of redshift, 7 to 9-ish. There was, sort of maybe some qualifications of other things where it was like, really, have you pushed that far? Redshift 11, probably not. But with JWST, I've already seen claims of a Redshift 20 galaxy, which is insane. I mean, in terms of time, it doesn't sound like it's pushing back that more. It's only a couple 100 million years, but that makes all the difference in terms of getting back to those first stars that were forming. So it's incredible to see all these images coming through from James Webb in real time, sort of being posted all the time to the archive where the Space Telescope Science Institute manages, the Hubble Space Telescope and the James Webb Space Telescope. That's another thing. People always say, we've had just these 5 images. Is that it? And I'm like, no, there's new stuff being posted all the time. It's just not being put out as a press release by NASA or anything. Seeing those images come in real time and then see sort of the community scramble to, analyze these first images we're getting because people are so excited to get their hands finally on this data. People have been working almost with, simulated data for so long that they were like, this is what James Webb's data is going to look like. So I'll build my tools to work on this. And then they finally can just plug in the real data and hit the ground running with the science. And it's just fun to see that happening and papers getting published all the time with these new this new kind of data, and also these new tools and almost like new phrases and terminology we're having to get used to as a community as well, and getting used to say things like Redshift 20 just being a normal thing that you could probe that you couldn't before.
So the people in charge of JWST and pointing it in the places where everyone wants to go. Presumably, this is like just 24/7 that they're having to do this like every single at the end of that observation time. It's on to the next, on to the next, on to the next, and you've just got to keep going and go because it's got this kind of limited lifespan. You're trying to get as much as possible out of it. Is there any sort of time set aside for sort of calibrating, upgrading, and all those kind of things to see if you can eke out a little bit more?
Yeah, definitely. All that kind of stuff is being set aside, as they go in terms of like if there is any tweaks needed. There's obviously a very rigorous schedule that's been set a few years ago now. Like I remember the proposal sort of tool being opened back in probably 2017, maybe 2018, to say, let us know what you would want to do with JWST. And obviously there's a huge influx from across the entire community of proposals put in that was way more time than they ever could have given out, and this will happen every year now. And they're working with that schedule of the proposals that were essentially successful. At the minute, they've got it to where, they want it to be peak performance in terms of what they know it could do and what they planned for it to do. But as they get to know the telescope better, there might be certain things that they can do in terms of tweaks to improve performance or in some way, or there might be some tool that can do some post-processing to improve it as well. So again, we're still learning as we go. You obviously design a telescope and you launch it, but working with the telescope you designed and working with the telescope that's actually currently working in space are two very different things. Yeah. And so I think at the minute it's still very much a learning curve for everyone involved, whether it is, the people who are doing the science with the images, or even the people who are just, in control of the telescope right now and sending the commands and getting that data back down. I think it's a learning curve for everybody.
Yeah, I mean, with something like JWST, every time a sort of new type of observatory is built, or a new, every time you sort of increase the power, particularly by an order of magnitude, there always seems to be a new phenomena in space that has everyone scratching their heads, like, things like FRBs and I guess the black hole in the first place, and so are we getting hints already that JWST might have started picking up things like that? Or do you think that that's not going to be likely with something like JWST?
I think it's very likely we'll get stuff like that. Yeah, I haven't heard hints of there being any what we call essentially serendipitous discoveries, like stuff that it wasn't planned for. Like JWST has been designed for loads of different science cases, and all of that is hitting us now and hitting headlines and everything. But in terms of serendipitous discoveries, I just don't think we can call what it's going to be. And especially, I think we could be making these serendipitous discoveries many years into the future on data that's being taken now, because the beauty of JWST is one scientist comes with this proposal that they're like, I want to observe this thing. Let's say it's supernova 1987A in the Large Magellanic Cloud or something, right? Let's say they want to observe this specific thing with one of the instruments on board JWST. The beauty of JWST is that as one instrument focuses on that specific patch of sky that target is in, all the other instruments are also taking light, but from adjacent patches of sky at the same time, like within the field of view of the telescope. So yes, you focus on the one thing that you plan to observe, but then you also get bonus data from the 4 other instruments that you didn't plan for at all in a random patch of sky. And I think in that respect, we're going to be, sort of still sifting our way through that kind of data in years to come. I think there's going to be projects that are specifically like JWST archival bonus data projects, because the scientist who applied for that one specific observation on supernova 1987A is going to grab that data and be like, right, I've got so much to do. They're probably not going to look at, the bonus stuff that they got. So this is why I think we can't call what JWST is going to reveal. And I think there's been so many times in history where people have been like, oh yeah, astrophysics, we're pretty close to figuring all that out, right? And then there's been this new surprise that we're like, oh, nope.
Well, I mean, yeah, the expansion rate of the universe. Oh, what's this? It's not just expanding. The expansion's increasing. I mean, and that's just a sort of weird 90s phenomenon. I mean, that just is that. I mean, it's just mind blowing. It seems to be an incredibly, and the amount of times I've said this on the podcast, it just seems to be, the last sort of 30 years of astronomy, it seems to be the most exciting time that has ever been, but just not in a kind of in the way that you'd expect it in terms of virtually any field of science. But it does seem as though astronomy is even more so than virtually anything else. I mean, like particle physics almost got bogged down, but astronomy seems to be completely the opposite. There seems to be so much going on and mainly driven by this, new technologies.
I think it's interesting that you said 30 years, because obviously Hubble launched in 1990, about 30 years ago, and that was the first telescope to have a digital detector on the back, one of these new CCDs that had just been invented, essentially because astronomers were calling for a better way of recording light from their telescopes. They didn't just want to use bulky photographic plates anymore. And so I think that's really what's massively benefited modern day astronomy, is being able to do that across the entire spectrum: X-ray, gamma ray, infrared, visible light, and those and radio, all of those observations improving with all of this new technology that's developed as well. So I think that's what's massively been the thing in the past 30 years. I don't know I think I'd argue whether it's not the most exciting time. I always say I would have loved to have lived during the time when, sort of Edwin Hubble figuring out that the Andromeda Nebula, as it was called then, was not in our own Milky Way galaxy, but was actually an island of stars in its own right. And all of these other things are islands of stars in their own right. And wow, the universe is so much bigger than we thought ever was.
You could also say Newton and Galileo. I mean, how amazing to be Galileo and go, oh my God, what's going on at Jupiter, and being the first person to see Jupiter's moons. I mean, that's just bonkers.
I mean, he also, with his telescope, was the first person to realize that the Milky Way, which was just this splodge across the sky, was made up of individual stars, that the light of which all bled together. So again, I think Galileo.
Galileo probably. Yeah, that was like a sort of early growth spurt. It's like a sort of, it's infants. Well, even then, it's not really the infancy, is it? Because you get back to the Babylonians, but
yeah, exactly.
It's crazy. But I mean, so much stuff seems to be happening, and you've got multi-messenger astronomy as well. I mean, presumably that must be incredibly important for your field of work. The things like LIGO and
100%. Like LIGO is really giving us the limits to black holes and neutron stars, and literally at what point does the neutron star become a black hole? What's that maximum mass? It's really drilling down on what that is, because as you get to that point, the theory it sort of gets a little bit like, well, we don't know, because we've never been able to, understand what matter like this is like. And you get all these relativistic effects that you have to take into account and everything. So LIGO is great in the sense that we can finally get observations on that. And also, in terms of gravitational waves, it's almost energy released by the collision of two black holes. And again, this comes into growth of black holes too, because you could have this merger of two black holes. That would be incredible. But then also, you have this idea of multi-wavelength astronomy as well. Not just seeing a galaxy or a star or anything like that in visible light, but across, the entire electromagnetic spectrum, and that giving you so much more information. So when we had the LIGO discovery of the neutron star merger that made a black hole at the end, but that because it was neutron stars, it gave out light beforehand. And it was the worst kept secret in the entirety of astronomy, because literally every telescope in the world turned to look at this thing, and everyone was like, there's nothing there though. Like, what could it be? It was, these are all these Twitter bots now as well. That's like, the Hubble Space Telescope is currently looking at this for blah person. And you're like, well, that person works on gravitational waves, so I wonder what that could be. It was the worst kept secret, but, having that idea of not just multi-messenger, but multi-wavelength astronomy on this one specific target, coming at it from literally every single, tool we have in our arsenal. And I think that's what the past 30 years has given us, is the ability to do that.
Yeah, it's just coming from everywhere, isn't it? All the different bits of data. I mean, that's a really interesting element of you've got this diary that James Webb is having to fulfill of everything it is. But yeah, you're right. Someone at LIGO could then phone up the peeps at JWST and say, right, I need you to look at this. Is that really annoying for the person that had diary time on the JWST?
I think it gets rescheduled. I don't think they're ever sort of like kicked off necessarily. That's the beauty of space telescopes, is that if there is something that has to be rearranged for, that doesn't derail an entire trip, for example. So I had time on the Isaac Newton telescope on the island of La Palma last year, twice. The first time there was a freak snowstorm. The first time it had ever snowed in Madrid for 50 years or something. It also hit La Palma and the telescopes froze shut. The second time, the volcano on the island of La Palma erupted. So yeah, these kind of things, if you're over there, if you're on a trip, it definitely disrupts. But with the space telescope, it's obviously all set, and you have all the observations teams that are sorting it out, that run the telescope day to day as well. So it's really out of your hands. Which is in one respect great. You're just sort of sat around waiting for data more than anything. You should have a bit of a longer wait, I guess. What's wonderful is to know that JWST is going to be a tool that is used like that. And I don't think anyone in the community would begrudge it. It's sort of someone calling them up and going, quick, no, look at this thing. And we've actually got that coming up with the DART mission as well, NASA's DART mission that's due to impact with an asteroid on Monday, the 26th of September. So I don't know when this podcast's going out. Maybe it's happened before then.
Yeah, just have happened. Yeah.
Well, let's hope it happened successfully. But I know that the James Webb Space Telescope will also be used to look at the asteroid system that it's colliding with, to look at the aftermath, essentially, of that impact, which is essentially a test to see if we could deflect an asteroid if an asteroid was ever a hazardous to Earth. The asteroid it's impacting is not a hazard to Earth. It won't be a hazard to Earth after the impact either. I feel like we should say that. And it's great to know that the JWST is just, it exists now as a tool. It's not something that the entire astro community are like, oh, when JWST launches, oh, when it's finally ready, and it gets pushed back and it gets pushed back and it gets pushed back. It's up there now, and you can go, yeah, let's use it to do this thing. And it's great to know that it's, this tool you can whip out the back pocket when you need it.
Yeah, I always currently, when anyone sort of belittles humans, I always think, well, let's have a just look at the James Webb Telescope that's out there orbiting a Lagrange point, and it's just this ridiculous piece of equipment that picks up the heat of something that happened 13 billion years ago. And you go, I think that's pretty good. I think that's it's incredible. You've got lots of different things that James Webb Telescope's up to, which is, even things like, I noticed recently they were pointing it at Jupiter to have a look at Jupiter. So you've got solar system stuff, you've got black hole stuff, you've got, other astronomical points. Is there a sort of pecking order of who like like the people in the exoplanets? Surely they feel as though they should get most time on it. Is there a pecking order of out there?
I don't think there isn't a pecking order. There's just the very standard proposal system that we've had in place in astronomy for a very long time, that you put in your proposal, and then the time allocation committee will technically rank the proposals. So maybe there's a pecking order, but it's supposed to be independent of field necessarily. Having said that, though, obviously JWST was designed to do various different things. There were sort of 5 main science goals, including, first stars and exoplanets and things like that. my field of very nearby galaxy studies in terms of the supermassive black holes in the center. I like to be able to resolve the shape of the galaxy around them as well, hence why they need to be nice and nearby. I like pretty things, not just little tiny pixel blobs. And that my field in that respect probably was left out of that, 5 main science goals, because it wasn't necessarily obvious what it would be used for in that field. It was very much being taught. There was a very much specific reason it needed to be an exoplanet, because they wanted to look at the atmospheres and things like water and carbon dioxide. Those kind of elements show up in the infrared, and first light, you can only see that light in the infrared. So it was obviously a very good reason to have it there. With my field, it was sort of like, well, we'll just wait and see what it can do once it's up there, to be quite honest. And I've already had that eureka moment of being like, oh, it can do that. I didn't even think, we could write a proposal right now. Let's get it to do this thing. So in the first images that it released, there was the image of the 5 galaxies all interacting, Stefan's quintet, 4 galaxies interacting, one in the foreground. And the one at the very top has this incredibly bright thing in the very center that almost looks like a star. It has that distinctive sort of 8-point star shape that we're getting very used to seeing with the James Webb Space Telescope. That's essentially the shape that's created as the light travels through the optic system in the telescope. And basically you really see it when something is incredibly, incredibly bright. And that star thing in the center is not the star, it's the supermassive black hole. And that's another misconception, is that people think black holes are black, but they're actually some of the brightest objects in the entire universe. I mean, it's not the black hole itself, because nothing can escape a black hole, but it's the gas that is spiraling around the black hole that is moving at such incredible speeds that it's heated up so that it essentially glows across, visible, infrared, light, everything. And so you actually see that light with JWST in the infrared, especially because it can peer through dust as well. So dust, just big lumps of, molecules of heavier elements like oxygen, nitrogen, that kind of thing. Like supernova poop is what I like to call it. That can block visible light because it's a similar size to sort of the wavelength of visible light. But infrared just happily goes around it. So as you peer into the center of galaxies that are very dusty, often it's hidden from you that the supermassive black hole in the center does have this gas swirling around it, and eventually will be, accreted, as we say, eaten by the black hole, if you will. And with JWST, it reveals it sort of in all its glory, that it's there, to the point where if you look at the deep field images from JWST and you look at all those tiny background galaxies, in some of them you can see that 8-pointed star shape. It's faint, but it's there. So not only are you seeing the shape of these very distant galaxies for the first time, but you also know there's a growing supermassive black hole in them. And you're seeing that back at higher and higher redshift earlier in the universe than we've ever seen before. And that's going to give us a much better idea of, how do supermassive black holes grow and at what rate, at what times in the universe. So seeing that was my I'm in love with this thing.
Yeah, no,
that it can do that.
Yeah, I do like its little signature. Its signature 8 points. Yeah, that's we got used to Hubble's, and then now you've got this. So you know kind of which telescope is giving you the pretty picture at any one time.
Because it's 4 points with Hubble, isn't it? Because it has a circular mirror. And James Webb has this 6-sided mirror hexagon with the tripod that gets in the way as well. So it ends up as an 8-point star.
I mean, that's incredible, isn't it? What I love about those. Look, the things that you've just mentioned is you've got these absolutely enormous objects, but of course, understanding them, and obviously that thing about black holes is that that everything's moving so fast and everything's so big, and the physics is so crazy that you're actually having to rely on sort of particle physicists and quantum physicists knowing what they're doing. So you've got these people working at the ridiculously small end and people like you working at the absolute, we're talking about these ridiculously huge objects, and yet to understand them, you kind of have to know both.
Yeah. And I mean, I think that's why I love physics, in a nutshell, is that you get to deal with the ridiculously small and the ridiculously large and everything in between. We joke that chemistry can be explained in a page of physics, and technically biology is just a tiny small corner of the universe that people are explaining. And, it's sort of the one true science to rule them all, to put a little Lord of the Rings reference there.
Yeah. You've got a book out at the moment about black holes. What made you decide to write that?
Yeah, I mean, it's called A Brief History of Black Holes. And as I said at the beginning, it's really wanting to challenge a lot of all the misconceptions that I constantly hear from people, being like, black holes are these hoovers, they're black, they're the brightest objects in the universe, Einstein invented black holes. No. And trying to get across that almost why we think what we do and how we figured out so much of what we know about black holes, and also reminding people that it is still in its infancy as well. And I think it just gives, through the history and almost the human stories behind it as well, you get a much better understanding for what they are. And I learned so much writing this book as well about how everything, fits in together and when things happened. And that was, incredible. And I think it was just a book that I've always wanted to write because I've always loved black holes and been fascinated by them. And just being able to share that, sort of the knowledge I have from all of the research side of things and then putting it together with that sort of human history side of things was fabulous. So I really hope people like it. It's got a beautiful cover. My publishers asked me, what do you want the cover to look like? And I was like, make it pretty and make it shiny. And I think they delivered on both of those fronts as well.
Excellent. When does the book come out? Is it already out?
The book is out now. Yes, it's out in hardback, like an ebook version, and also an audiobook version, which I narrated myself.
Oh wow!
As well, which was really fun.
Oh wow, that must have taken you. How long did that take?
3 days.
Oh,
3 days. Yeah,
that's hard.
Only because I wasn't allowed to talk at my usual very fast pace.
How to do it? Yeah. Did someone sort of take your first chapter and say you've talked too fast?
They were prepped ahead of time and they were like, okay, so remember, slow
Brilliant.
down.
Yeah, that's awesome.
Right.
Yeah, I'm going to immediately download that. I didn't realize it was on Audible. I'm going to definitely download that for my car journeys. I love Audible books for that kind of stuff. The only problem with is it's quite hard to sort of skip back when you've said something amazing and I'm driving and I go, what did you say? that's my own, that's the only annoying thing with that. So yeah, you were writing. So you've written this book about black holes. When you're doing your research, because often, obviously, the way I do the podcast often is I'll have something like, I'll be looking at news stories from Nature or something like that for the latest kind of science papers on a particular subject, and I'll try and wade through the actual science paper itself. But I often notice, obviously, you get the abstract, and it's quite easy to understand, and then it goes into the actual how you've done it, and it's incredibly complicated, and you go, what on earth's going on? Do you ever, when you're actually working and you're kind of, everything seems a little bit abstracted, and it sort of goes into maths, and it obviously goes into statistics, and you're just really sort of number crunching data and sticking things into computers. Is it always really nice to then go back and actually sort of try and tell the story of what's actually happening rather than just it being a bunch of numbers?
It can be, yeah. And it's one of the reasons I love making videos for YouTube as well, is that it's a very creative process, and also it's a very short-term process. Research takes a really long time. Like, you can be working on a project for a year or more, whereas my YouTube videos are one a week and I'm done, That's off the desk. So that's nice. And that's another reason why I love the book as well, was sort of that very creative process of writing. As opposed to the very dry sort of scientific writing that it's very, concise and to the point. You could have a bit, obviously, more fun with it and stuff like that. So it was nice to just have the juxtaposition, but also to be able to work my own sort of research into the book as well. Because I think that was always so important to me, was you're going to do a history of black holes, you've got to get to where you are now and say, here's all the stuff we still don't know and the stuff we're still working on and trying to answer right now as well. So being able to marry the two was really, really rewarding.
Yeah. So after over the last few years, say, where in your field, what are the sort of things that you've been working on? What are the questions you've been trying to answer, and what are the sort of questions that you have been answering and feel as though that you've got a pretty satisfactory answer, even in the sort of recent history?
Yeah. So I've got two big questions I work on right now, and one is, can supermassive black holes kill galaxies? in essence.
Nice.
So if you have this very turbulent region around a black hole where you've got gas spiraling in, getting very, very hot, you can end up with the black hole doing an almost sort of burp of energy outwards. We call these outflows or jets. Sometimes they've got magnetic fields get involved, and it's not an energy from the black hole, it's from these very turbulent regions around it where it's almost there's too much pressure there and that has to be released. That expulsion of energy can travel throughout the entire galaxy, we think. Theoretically, we need that to happen because essentially what we think happens is that it removes the gas you would need to make new stars, sort of the shockwave through the galaxy. And then you stop all this star formation, and then a galaxy doesn't grow any bigger. It starts to die off. And we need that to happen to essentially make our simulations of the universe match what we see in the observed universe. But we've never actually observed any evidence for that happening across sort of the entire galaxy population. We've seen sort of very niche, like in one galaxy this happened, but in this galaxy this happened. And that's basically one of my questions, is trying to prove that that's happening on a big galaxy-wide scale. So that's very much big statistics kind of work. My other question I look at is, how do supermassive black holes grow? Because for a long time, the one way, or the way that was thought to dominate their growth, was that you have two galaxies, each with a supermassive black hole in the middle. Those two galaxies collide and merge, and the two black holes in the middle will collide and merge. And therefore, basically, like, you could double a black hole's mass in that way. So that was sort of the one idea, because you could see this really like clear correlation between the mass of a galaxy and the mass of a black hole as well. But my work actually showed that you still get that correlation in a galaxy that's never had a merger before. So something that is pure spiral galaxy, left on its own its entire life. It's never been disturbed. It's very happy as it is. Still got very massive, supermassive black hole. So you say, well, okay, well, how did they get that big if they've never had the merger, which is the dominant way we think that they grow? And actually, my research, slowly but surely, has overturned this idea, along with all my collaborators as well, across observational work and simulation work, sort of showing that actually galaxies seem to be able to grow their own black hole, sort of in a very slow and steady tortoise style wins the race. And that is actually the dominant way it happens in between all these big galaxy mergers that seem to sort of, distract us all, because they're the sort of the big lights.
Are they like sort of the galaxy mergers? Are they sort of a shortcut to it? And presumably, like you said, they lose their nice spirally shapes. They're a bit more boring, aren't they? The sort of those
blobs.
Yeah, blobs. Whereas, you're seeing these absolutely enormous ones in these pristine galaxies that have remained. Yeah, that's super interesting, isn't it? Have you any idea how that happens?
Yeah, so we pretty much got to the point where we're like, okay, we're pretty sure this is the dominant way it happens, but we have no idea how or what's going on inside the galaxy. So that's basically the next stage now, is sort of saying, okay, is it, say, the spiral arms funneling gas down them towards the black hole? Or is the galaxy somehow able to take like cold gas from the sort of what we call the galaxy halo around it, where there's no stars, but there's just this sort of like big lump of gas, because it's gravitationally attracted to the fact that you've got this big galaxy there that's very massive as well. Or is sometimes you get this bar structure through galaxies. I don't know if you've seen this, where this is a long, thin thing and you get the arms out of the ends. Maybe that somehow funnels gas down the center. And so there's lots of different mechanisms we think could do it. And in simulations, maybe it looks like they could do it. But proving that is obviously, with observations, is the really difficult thing. You have to look to see if you can see some sort of gas flows in the galaxy. Or you can sort of say, okay, well, how much is the black hole growing by and throwing out? How much material is it throwing out? How much is it growing by? Therefore, how much does it have to be funneling to the center? And what processes do simulations say can do that at that rate? There's lots of different sort of angles that you can come at it from, because there's loads of questions that we still don't know. Again, reminding us that this field of research is definitely still in its infancy, 20 years maybe. And that's it in terms of supermassive black hole research. So long way to go. So you've got the supermassive black hole at the center of galaxy, but that's not it, is it? I mean, like the galaxy itself is actually just full of black holes. There's lots of stars that must have been popping their clogs and collapsing into black holes. Do they actually sort of migrate down towards the center of the galaxy, or like the solar system, if the sun was replaced by a black hole, everything would just carry on orbiting just like before? But is that the case with black holes? Do they swarm towards the center, or do they roughly stay where they're supposed to stay? Nope, just like stars, they'll stay where they're supposed to stay. And this is the big issue with how do you grow a supermassive black hole, is even the gas will stay where it's supposed to stay, unless there's some process to set it tumbling in. And so it actually, if you said then, if you replace the sun with a black hole, if you took the sun completely out of the solar system, the whole thing would completely fall apart. The planets, asteroids, comets would ping off everywhere, right? Because the sun is like 99.999 whatever % of the mass of the solar system. Take the supermassive black hole out of the center of the Milky Way, and the galaxy would be completely fine. Because it's would be held together by its own, what we call self-gravity. So there's a reason why the Milky Way just isn't some giant big gas disk swirling around the supermassive black hole in the center, is because gravity, in the local regions where stars form, is stronger from the gravity that's pulling from the black hole. And so that's why you make stars in the first place. Otherwise, if you didn't, everything would just end up in the black hole in the center. So yeah, even if you remove the supermassive black hole, it's such a minute, maybe not even 1% of the mass of the entire galaxy. Even though it is supermassive, it's still very small in comparison. So, the galaxy would be absolutely fine. And this is why we have such a big issue on how do supermassive black holes grow?
Yeah, I mean that I have to say that's a great fact. I've never even thought about that. I'd just assumed if you removed it, it would cause chaos. But yeah, that's. And presumably those stars that orbit really close, the ones that sort of go whizzing past, presumably they're doomed. But
no. Again,
even they're not.
Unstable orbits, exactly.
Oh.
Even there was this weird gas cloud that we thought was doomed that was on its way towards the center of the Milky Way, and that somehow looped around unscathed as well, fairly close to the black hole. And so it just reminds you that until you get to that point of no return, you can always, especially light and gas and stuff like that, it can still make its way out of there. I mean, it was very spaghettified coming out. It's very stretched out, this gas cloud, but it still made it out. And so I think it's these kind of misconceptions, and also this idea of self-gravity I cover in the book as well, just because, people haven't stopped to think that if it wasn't for self-gravity, we would just, we wouldn't be a galaxy of stars. We would just be a big gas disk feeding the black hole at the center.
That's really cool. Yeah. Is there anything you'd like to cover?
I think the one thing we haven't talked about that I loved learning about for the book was where the term black hole comes from. How you go from people talking about gravitationally completely collapsed objects in the 60s to the phrase black hole. It's sort of one of those things that people took on board because of its pithiness and its advertising value, I think it was described as. But it's actually probably the phrase that I think causes the most misconceptions for people. Because, first of all, they picture a black hole as a hole, and it's couldn't be further from that. It's this sort of three-dimensional object almost that started life as a star, which is a 3D object. It just collapsed it down.
Interstellar did quite a good job of trying to change people's view of what a black hole might look like, right?
Yeah. Yeah, it did. It had that amazing sort of render of a simulation that was fantastic to see. It was so, so cool on seeing it. But yeah, the phrase black hole, I don't know if you've heard of the Black Hole of Calcutta.
A
very sad part of history, essentially a prison cell that was about the size of 3 double beds put together, where a very large number of people, British soldiers, were imprisoned in it, and like a good fraction of them didn't survive the night. And there is, memorials across Calcutta in India today to the Black Hole prison in Old Fort William in Calcutta. And there was a physicist called Robert Dicke who apparently with his family, when anything went missing in their house, they would say, it's gone to the Black Hole of Calcutta. It's gone missing. And he started to use this phrase to refer to these gravitationally collapsed objects in the sense of this sort of like crush of matter, referring to this crush of bodies in the prison. Rather morbid. Of a phrase, but I think a lot of people have heard of the prison, but presume it got its name from black holes, when in fact it's the other way around.
I always thought it was something glib that Fred Hoyle said on a radio show.
No, that's the Big Bang.
Oh, was it Big Bang?
Yes,
right,
Fred Hoyle dubbed the Big Bang as something sort of very, again, like a pithy title to try and get across the meaning of it. Again, causing massive misconceptions about what the Big Bang is as well.
Yeah. In fact, before we started recording, you were moaning about this idea that in the press at the moment, everyone's moaning that
press is a kind word for them.
That JWST has discovered that there was no Big Bang.
Yeah, the Big Bang didn't happen. Is the headline.
Give us a quick rundown about how that misconception's come about and actually how ridiculous it is.
Well, the headline itself, the Big Bang didn't happen. There's so much to unpack there, because people think the Big Bang was this moment of almost creation, at time equals 0 in the universe's lifetime. And that's not what the Big Bang is. The Big Bang theory describes how the universe has evolved from a very hot, dense state to the cooler state that we see now with all the structures that we have, the galaxies around us. So the Big Bang Theory is essentially 13.8 billion years of evolution of the universe. So to say that didn't happen when you can see the entire the universe around you is absolutely perplexing and mind-boggling. I mean, if they're referring to this idea essentially that James Webb is seeing galaxies, spiral galaxies, especially these sort of isolated, beautiful, sort of left their own devices galaxies earlier in the universe's history than we ever thought that they could exist. Of course, our models of when we thought they could exist were based on Hubble Space Telescope data, which can only see so far, and things start to get blurry after a certain point. So we couldn't resolve the shape of these things. So yes, of course, as we get new data, we need to improve our models. But for some reason, there's this narrative, well, the Big Bang must have never happened if this contradicts with our current models. But it's like, no, that's just how science works. You base your theories and your hypotheses on the evidence you have. And when new evidence comes to light, you go, okay, well, something needs to change. And in this instance, it will be a tweak to, how galaxies immediately start to form and what fraction of dark matter and normal matter is there and all of this kind of stuff to enable a spiral galaxy to form very early in the universe. It's not going to be some massive change to, the entire idea of what the Big Bang was or is. And so it's sort of a misunderstanding of the scientific process, I think, is what it is.
Do you know what? I actually think it's probably one of the biggest. As a science communicator, it's the one that you come across the most, isn't it? That's probably the most irritating, is this idea that our scientists said this and now they're saying this, as though somehow they're disconnected. And it's like, well, one is really just a refinement of the other. And yes, that people didn't understand it, but the whole idea is that we can drop our dogmas and move on with when go, oh, well, that was wrong. And I have to say that is one of the best things about your YouTube channel, is that you pretty much do that every time that you're on, is you're dealing with one of those kind of things and working your way through it in a really, I think, exciting and constructive way. I really don't like the YouTube channels that are kind of taking the mickey out of people for thinking things like that. But it's more of a kind of, well, you can just explain it rather than be annoying about it.
Yeah.
But well done, because I really do like that sort of that style of science communication. Anyone who hasn't seen your channel should immediately go over and start watching it, because it is absolutely brilliant. And get the book, which I am immediately going to do on Audible as soon as we finish. So thanks very much for coming on.
Oh, thanks for having me on. It was a delight.
The Interplanetary podcast is alive!
There we go.
I don't know why. A lot of my friends who know that I do like space ? They're like, oh, Linn's able to explain black holes. I'm like, I really kind of can't. I do planets. I know that they exist, and I know maybe more than the average person, but I really don't know a lot. So it's really cool to listen to people who know so much.
And this is when you listen to that interview, you realize actually, she's done some very serious research on supermassive black holes, and it's like hence she wins awards and stuff. So
it doesn't come out of nowhere.
Not only is she a great science communicator, but she's also like, kicking ass in the field as well.
Exactly.
So that's good.
Again,
so that's
feeling
amazing.
very insecure.
Yeah. Your time will come, Linn, I'm sure.
My black hole, black hole chapter.
Yeah. Oh, so talking of black holes, supermassive black holes, I thought I'd find a supermassive black hole story for the week.
Oh yeah.
Just to follow it up. So I saw on the normal place, space.com, there was a story about there's a black hole, the supermassive black hole at the center of the galaxy called
Sagittarius A.
So Sagittarius A star.
Oh, all right.
You
Sorry, Dad.
has got a supermassive black hole. The supermassive black hole has got a hot spot whizzing around it. So it's got this kind of what they think must be like a sort of bubble of hot gas that's in orbit around the star. That's what they think. I mean, there's a paper out that if you can go directly to the paper called Orbital Motion Near Sagittarius A Star, Constraints from Polarimetric ALMA Observations. So that's by M. Weiglas or Welgus et al.
Again,
And
nobody's allowed to comment on our pronunciations.
Yes, I'm afraid not. But it's, they've kind of spotted this very, very bright, hot gas that's whizzing around, kind of at sort of, if Sagittarius A star, even though it's millions and millions of times heavier than the sun, in fact, do you know how many times heavier than the sun it is?
No, I don't. Tell me.
4.3 million times heavier than the sun. It's because it's a black hole. It's actually not that big.
Yeah.
It's actually not that big at all. So
it's very compact.
It's very compact. Yes. So it's actually not that wide. So this hot gas cloud is orbiting about sort of like the Mercury's orbit. So if you replaced the sun and stuck Sagittarius A star there, then this gas cloud is very close to the accretion disk and everything. In fact, kind of part of it. So it's kind of that's spinning around. But what's interesting about it is that they think that kind of then suggests that the accretion disk itself is going around in a certain direction.
Oh, okay.
Yeah.
Interesting.
So I think obviously it requires more data.
What's my catchphrase? More observation time. Woo!
Well, yeah, it seems that means that that it sort of says something about the sort of overall black hole system.
Yeah.
So they're kind of honing down about what Sagittarius A star would be like if you were to get anywhere near it. Yeah.
Terrifying is the answer. I could tell them that in 5 minutes. They didn't need all this data.
Well, literally, absolutely terrifying. Yeah. I mean, it's not that big as a supermassive black hole, although I'm sure it is very, very big.
But I know what you mean.
But the one at the center of M87, of course, is much, much bigger.
Yeah.
But it's one of the I always think the craziest thing about supermassive black holes, and I should have asked Dr. Becky about this, is there's the tidal forces thing where you get near a black hole. If you get near like a normal black hole, you get spaghettified because your feet are that much closer to the black hole than your head that the tidal forces are much stronger on your feet than they are on your head. So it literally pulls you into spaghetti.
Yeah.
But the same doesn't happen with very big supermassive black holes because the tidal forces aren't, the variation isn't as big.
Sure.
So if you were to fly, if you sort of if you fall into a supermassive black hole, you actually, other than like having to go through the accretion disk and obviously be burnt to death, etc., all of that bit, all that horrible stuff.
Yeah.
If there was no accretion disk, if there was no other matter, you might not even notice going over the event horizon.
Wow.
But if you were being observed, anyone seeing you going over the event horizon would see you sort of freeze at the event horizon. So if you were to look back out when you were going in, you would see the whole future of the universe in one go.
It makes me feel a bit nauseous to think about.
Black holes are strange, aren't they?
Do you know what I did recently, by the way? I finally caught up to 1989 or whatever and read Contact by Carl Sagan. I hadn't read it before.
Do you know what's really weird? I rewatched the film Contact at the weekend.
Oh my God. Well, how about that? I haven't seen the movie. Should I watch the movie?
Oh my God. Should you watch the movie? Absolutely. It's aged really well.
Really?
Do you know what? I almost was going to say at the end of this podcast how if anyone hasn't watched Contact, watch it. I'd actually forgotten how brilliant it is. It's so good. I know what I'm
doing this weekend then.
Yeah. It's really good. In fact, I might go and read the book. Now that
there you go. I read the book.
Yeah,
you watched the movie. We'll swapsies.
Well, swapsies. Absolutely. It's so good. It's when Matthew McConaughey was good before he went through his bad patch.
Ouch.
We went through a bad patch, didn't he? Where he was just dreadful for a bit. Yeah. It was weird because I don't think it was that well received at the time, but it's so good.
The movie?
It's got John. Yeah. It's got John Hurt in it. It's got Matthew McConaughey, Jodie Foster.
Just very cool, right? I mean,
Tom Skerritt. Oh my God, it's really
good. I didn't know this because, spoilers, I mean, the black holes are featured in this, and tidal forces. I mean, at least in the book, they are discussed. I don't know how much detail they go into.
No, it very, very, very little. In fact, they don't. In fact, it's just wormholes. And as we just heard from Dr. Becky, there is a difference between wormholes and black
There
holes.
certainly is, absolutely. Well, how about that? Yeah, I mean, what a good movie tip.
The only thing that made me a little bit sad is that, of course, a big chunk of it is filmed at the Arecibo Observatory. That did make me a little bit sad. However,
don't you just love astronomy? It's almost like you dedicate this much time to making a space podcast. Do you like space, man? Do you like space?
well, the great thing is, I actually thought, God, how ace was Carl Sagan?
Yeah.
I mean, it's like not only he's another, what a great science communicator, but to be able to write a book like Contact as well.
Yeah. Well, I really enjoyed it because, I mean, I dare I say it? I mean, I am a professional astronomer. That is my job. Mm-hmm. That's how I make my salary. And so I thought it was really cool to read it as well because I did think that it felt throughout quite realistic for such an unrealistic premise, let's say. But yeah, I just thought it was really, really cool.
Yeah, there's some brilliant bits. He's making lots of commentary about lots of different things. He's very even-handed with his people of faith kind of thing. But
let's say it, female protagonist, cool move by Carl Sagan.
Has to be said, that was one of the things that made me think, God, this is a film with a proper female protagonist.
It's not like
that's
funny.
Not
it's funny because she's smart and a woman. Whoa.
Yeah, there's none of that in it whatsoever. Yeah, it's absolutely brilliant.
Yeah.
It's so good. Yeah. What an absolute legend. But yeah, it's got things about trying to get funding as well, and like being taken seriously as a young as a young kind of scientist and all those kind of things, and not working in the right field that your professor doesn't want you to work in, and all those kind of. So it's really good. Yeah, it must have been brilliant for you because it must have
I really enjoyed it.
Resonated loads. Yeah. What are you up to? What are you up to in the next few weeks?
Mostly weeping because I have loads of work to do. and let's be transparent. You know, this is your bread and butter as a researcher is writing papers, which is really fun until your work doesn't do what you want it to. But no, it's good. I have a lot of conferences. I have a lot of traveling to do. I might have something fun for next month's podcast, but I'm not going to give any spoilers. We'll see.
Just in case it.
Just in case, like I drop dead in the next 24 hours or something. Like, let's not promise anything.
You don't want to jinx it.
Yeah. Okay, that's me knocking on wood. Actually, that's plastic. Crap. There's no wood in here. Okay, my head will have to do.
Well, anyway, everyone will find out what that is because it's going to be super exciting.
Exactly.
Yeah. Nice. Well, that's it. I think we should say bye-bye to the Spodcats because we've probably spent far too much discussing not discussing space.
Would you like to thank our Patreons?
Thank you so much to Paul Hilton, Ian Holland, Dr. Bob Hodges, Bob Moore, Malta Keisling, Alden Vala, Marissa Davis, Mark Schoen, Ben Guthrie, Ronald Hatcher, Tupper Hyde, Neil Hansen, Tyrell McAllister, Gene Watchtonik, Kenton Hokanson, Jacob Economy, Seth Haberlein, Mark Huber, Joseph Jude Biernet, Nicholas Gillenstein, Adam French, Jim the Bing King, Steve Croucher, and of course, Mark Kelly. Well, there you go. Thank you very much, patrons. And I cannot thank you enough either because obviously you keep this running. You pay for the hard drive, you pay for the SoundCloud, you pay for everything. So thank you very much indeed.
Thank you very much.
Yes, and you know that I love you. And of course, you can always join in with the Discord where we have crazy channels in our Discord, like the AI channel where we. Well, as discussed last time, and a little crazy music channel as well. You can just
hell yes
open up a channel and just chat amongst yourselves.
talk about how disgusting our Greek pronunciation is.
Yes, it was a bit awful, and a massive shout out to Anthony and Jake who had me on their off nominal podcast the other day.
Oh, cool! I didn't know that.
Yeah. So that was super fun. It was super fun. We got to talk about SLS, which I can't. I just can't bring myself to talk about.
It's like how many years?
Oh my god! It was supposed to fly in 2016.
I remember like being almost a teenager. Like, well, I guess I would have been.
It's back in the hangar. It's actually back in the hangar again. It's back in the VAB.
I saw a tweet. I think it was Eric Berger who had said a tweet saying like, I foresee the launch for early 2023. And it was so ripped on at the time, when he tweeted it, which was in 2017. And people were like, that's absolutely ridiculous. Like, there's no way. Are you crazy? And I was like, wow, it's like second half of 2022. Not that many launch ones left.
Yeah, do you know, it's funny because there was a little tweet exchange between myself and Eric Berger, and what his response to one of my tweets was he doubts that he'll see humans ever launch on SLS. And that keeps getting retweeted all the time out of our feed. So it's one of those things. It's like, yeah, I mean, you've got to be pretty brave on the second attempt to go up on SLS. Oh, man.
I mean, yeah, we'll see how much long. Yeah. Question.
Which actually, with all of this, it does make you realise just how amazingly crazy it was that they did a manned launch on the STS-1, the first space shuttle. I mean, that just wouldn't happen. There's no way that would happen today, is there?
No way. I mean, and like, thankfully so, I guess, but...
Yeah, and John Young's heartbeat never went up. So he's being monitored and it just stayed at 80. That's how cool John Young was. It's just ridiculous.
I don't think my resting heart rate is 80.
No, his resting heart, his heart rate while piloting the crazy space shuttle was lower than my resting heart rate. Yeah, ridiculous. What a ridiculous human being. Anyway, that's it. Then I'm going to say bye-bye.
Thank you so much for having me.
Bye. Podcast.